Thank you so much. Can I see my slides? Oh, yeah. Great. I'd like to thank organizers for giving me an opportunity to talk about my works in this exciting workshop. And I'm very happy to travel back to Korea. I'm surprised to see like this beautiful building and cities. Okay. So I originally planned to talk about topological material search with symmetry indicators and fitting anomalies, but I also wanted to talk about some other stuff I was recently thinking about. Okay, and so let me start. So it's needless to say there are many materials in condensed matter systems, and there are many symmetry groups, and their combinations produces countless number of materials. So it better have some unified understanding and classification. Also, like that will tell us which material will be topologically interesting and which material will be featureless, right? So we want to have some unified classification. Now, one way of classifying systems is based on like a low energy spectrum. So here, like I show you just some example of low energy spectrum. So this is like a model of spin 1/2 Heisenberg model, spin 1 Heisenberg model, and spin 1/2 so-called Magenta-Gauss model. So their Hamiltonians are like this, standard one. In Magenta-Gauss model, you have nearest neighbor hopping, nearest spin interaction with amplitude half of the nearest neighbor interaction. If I diagonalize these Hamiltonians for finite size system under periodic boundary condition, I find this kind of spectrum. Okay, so you have a ground state, and you have a fast excited state, and this gap. You always see this kind of gap, but their scaling is different. For S equal 1 Heisenberg model, this gap doesn't close in the limit large L, right? But for S equal 1/2 Heisenberg model, this gap goes to 0 as a function of system size. So this is gapless system, and this is gapped system. Oh, this is very difficult to use. Okay. And in the case of a Magenta-Gauss model, you have ground state degeneracy. So you have two ground state, degenerate ground state, and these originate from symmetry breaking of translation symmetry. So you have dimerization. Okay. So you can classify these phases based on their symmetry breaking pattern and their presence or absence of gap and degeneracy. So you first ask whether the system have Hamiltonian with symmetry group G. The ground state have symmetry breaking orders, or there's no symmetry breaking. And when symmetry breaking occurs, you want to know the residual symmetry H. And then you ask whether you have excitation gap or not. Like for example, when continuous symmetry is spontaneously broken, there's a Goldstone excitation, so it gives you a gapless ordered phase, right? So, but there can be still gapped ordered phase, right? So that gives you this kind of classification. And finally, you ask the degeneracy. So if the degeneracy can be explained by symmetry breaking, or if there's no degeneracy, you may call the phase like a short range entangled phases. But if ground state degenerate without symmetry breaking, or if the degeneracy is more than you expect from symmetry breaking, then the phase might be long range entangled phases. And this long range entangled phase is very interesting. Like you have fractionalization, and you have anyons, and that example includes like a fractional quantum Hall state or spin liquid, or recently people discussed fractal topological phases. And the short range entangled phase is more common phases like topological insulators, SPT phases, and it also includes just trivial phase. Okay, and people usually classify like short range entangled phases, which has unique ground state with excitation gap, using this kind of continuous deformation. So you say Hamiltonian H1 and H2 belongs to the same phase if there's a path connecting these two phases without symmetry breaking or without closing gap. And so this kind of procedure gives you a classification of the phases or Hamiltonians, and suppose you have these three phases in the model, in the classical model you consider, and trivial phases are connected to real space product state. So in this diagram, phase H1 contains product state, so it is trivial. Phase H2 also have product state. Although these two product states are different, both of these two phases are trivial. And phase H3 doesn't have product state, so this is non-trivial phase, and it has irremovable quantum entanglement. Okay. And one way of diagnosing this kind of topology quickly, but only partially, one method is known as symmetry indicators. And here I want to discuss a simple example of spins in a ring. So I have in-plane spins. So the direction of spin is constrained to just u1 direction, and the spin is on the ring, which is also u1. So I can talk about winding number of the map u1 to u1, right? And in order to compute this winding number from the definition, I need to know the spin configuration continuously on the entire ring. However, in the presence of additional symmetry, like for example, like rotation symmetry about this axis, then spin at this position is related to the direction of spin at this position. Like these two spins are mapped to each other under spin rotation symmetry. In this setting, you realize that there are two special points in space, the spins on the axis of rotation. So these symmetric points, if you look at the direction of the spins at these symmetric points, you realize that you can tell the parity of winding number just by looking whether spins at symmetric points are pointing in the same direction or opposite direction. So the winding number is even if the spin points in the same direction, and the winding number is odd when the spins at symmetric points are in the opposite direction. And the latter case is interesting because the winding number cannot be zero. The odd winding number implies that winding is always non-trivial. So this is a simple but partial diagnosis of topology. And this kind of phenomenon occurs in band insulators. Huh? Oh yeah. In this case, because like I have rotation symmetry, and the rotation eigenvalue is say plus I or minus I, depending on the direction of the spins, right? Rotation is like if you diagonalize in that basis, plus I or minus I for spins. Yeah, so eigenvalue is plus I or minus I. Yeah. Yeah, so you can say direction of spins, but it's what I mean by that is a representation actually. Thanks for the question. Other questions? Okay, good. And okay, there's another easy diagnosis of topology. So that is done by Lipschitz-Matz theorem. So this theorem is a necessary condition to realize unique ground state with excitation gap. So like S equal 1 spin, Heisenberg spin, right? So if this condition is violated, it is guaranteed that there must be some degeneracy or gapless excitations. The most famous setting for this theorem is a U1 symmetric system with translation symmetry. So in this case, you know that filling is a charge by initial. That must be integral. So for example, like band insulators with fractional filling must be gapless. So that's kind of well-known fact. But for example, fractional quantum Hall states in which filling is fractional has to have topological degeneracy because there's no symmetry breaking, but the system is gapped. So the only way out is topological degeneracy. Similarly, recently there's a development of Lipschitz-Matz theorem in a system without U1 symmetry, but with a finite group symmetry group G. And in that system, the condition to realize a unique ground state is that all projective representation must be kind of removable. So for example, if you have spin one half spins per unit cell, like a projective representation per unit cell of say spin rotation symmetry. So this is like a irremovable projective representation. So you cannot have unique ground state. So either gapless or degeneracy. So that is S equal 1/2 Heisenberg chain or Majanda-Gauss model. You may understand a famous toric code model with some special symmetry from this theorem. Okay, so the message is that the violation of Lipschitz matrix condition in symmetry gapped phases guarantees that the phase must be topologically degenerate. Okay, so this might be a way to use Lipschitz matrix theorem in search for topologically ordered material. Okay. So what I want to talk today is the first topic is further developing a symmetry indicator method for superconductors. So like we have a big success of symmetry indicator method for topological insulators. So why don't we do the same thing for topological superconductors? That's the first topic of today's talk. But I also talk about more about this kind of quick diagnosis of topology based on symmetry indicator method or products, like ground state degeneracy on torus. Symmetry indicators, as I stressed, is only a partial diagnosis, right? Like we know that even if indicators are trivial, there's we know that there can still be topological in non-trivial phases, like Chan insulators or fragile topologies. But today I focus on like superconductors without symmetry indicators. Okay. So the first topic. So this is this work. Main contributor is this my student Seishiro Ono. So he's in my group, and he's getting PhD soon. So I think he's starting his application for postdoc. So I hope you kind of invite him to give a talk in your group. Okay. So as I said, symmetry indicator method for topological insulator made a big progress in the search of topological materials. So so again, this is like a momentum space, and I have in momentum space. Suppose we have inversion symmetry. Then there are like 8 symmetric points in momentum space called time reversal invariant momentum. And so these points are invariant under momentum, under inversion symmetry. So you can define inversion parities, inversion representations. And suppose the product of parities at this time reversal invariant momentum is odd. Then like this Fugate formula for Z2 symmetry, Z2 topological insulator says that this band insulator must be topologically non-trivial, like a Z2 non-trivial insulator. So this is like a famous story, but now like this kind of relation between representation of occupied bands and topology is extended to like all space groups or all magnetic space groups and various type of topology, like not only Z2 topology, but higher order topology or Chan insulators, whatever. And these extensions are done by many people, like including us, like a Princeton group, and also like Robert, who gave a talk on first day, and also Chen Fan made an important contribution. So, so symmetry indicators for topological insulators have been investigated by many people, and this method can be combined with like a DFT calculation. So you use material data as an input, and you perform DFT calculation and see representation in momentum space at high symmetry points, and that gives you topological data of the material. So using this idea, people conducted comprehensive search for topological material using the material on the database, and they form a result in the form of a database like this. So you click the material name, and you can check that their topological property, right? Now, this is very useful. So we wanted to do the same thing for topological superconductors. People say like topological superconductors might have application for, say, quantum computers, whatever. So it might be good to have material candidates. But what is difficult is that if we want to extend this kind of story to topological superconductors, there are two modifications. Okay, we need to consider. The first one is that the index we can define at each point in momentum space is different. So for insulators like class A, A1, A2, you have Z index in 0 dimension. So this is like a point in momentum space, right? So this Z is really the number of occupied band. So you can count the number of representations, say for parity odd representation. But for superconductors, you need to look at, say, like BD1 or D. Then the index is not Z, it's Z2. So there is, the type of the index you need to deal with is now different. And also, like you need to use a pairing symmetry as an additional input for the computation of symmetry indicator. And so what is pairing symmetry? So pairing symmetry is defined as, in the following way. So I have these like a BDG formalism. This HK is a Hamiltonian of the normal phase. This delta K is a gap function. And this is a symmetry representation of this BDG Hamiltonian. And in order to implement this symmetry group, symmetry G, HK and delta K must satisfy this relation. In particular, the transformation of this gap function, this quantity chi G, form a one-dimensional representation of space group. And this chi G is called pairing symmetry. So if chi G equal 1 for all symmetry elements, we say it is conventional. Like S-wave BCS S-wave superconductor is like a conventional example. But when this is not equal to 1, for example, -1 for inversion symmetry, then it is called unconventional pairing symmetry. Okay? And usually, unconventional pairing symmetry is a recipe for topological superconductors. And after some calculation, you can convince yourself that like symmetry indicators are all trivial if you assume conventional pairing symmetry in time reversal symmetric cases. So that's why like we investigated symmetry indicator for materials for each assumed unconventional pairing symmetry. So this calculation is done in this paper. And so what we did is, and our result is summarized in the form of like a database like this. So what we did is the following. So you select material like this, and then you also select a chemical potential. And then you also have to assume which pairing symmetry you want to consider, like S-wave type or P-wave type in the case of inversion. But for more general space group, you have to select which pairing symmetry you use as an input. Then this database will tell you the symmetry nature of the topological superconductor, symmetry nature of superconducting phase. So it is not as useful as a topological insulator story, because this is not like the table of this material topology is blah, blah, blah. It's not like that kind of nature. This table is like really like for this material, if the pairing symmetry is this, the topology is this. If pairing symmetry is this, the topology will be that. So this kind of table is now available, and we want experimentalists to use this result like back and forth method. Like the result is this. So what is the pairing symmetry? Okay, according to this table, okay, it means no doubt superconductor. That means this assumed pairing symmetry is not correct or something. Still this table is useful in checking or confirming the assumed pairing symmetry is correct or not. Okay, so that's how you use this result. Also, like we have a subroutine, and here. So previous database is like about the known material on the database, but this one is for new material. So if you have synthesized new material, you do DFT calculation, and you input your DFT result here, and you select the symmetry setting, like if you have time as a symmetry or not, then it will give you a calculation of topological superconductor. Calculation of symmetry indicator for superconducting side. Okay, so this was a story about symmetry indicators. Yes? Oh, yeah. I'm assuming weak coupling of superconductors. So weak coupling assumption means that just knowing the band, band structure of the normal phase, you can deduce the symmetry representation in the superconducting phase. So the assumption is that we never know the BDG Hamiltonian in detail. So we need to compute topological nature of superconducting side based on the band structure of the normal phase. And that is possible only when the gap size is not that big and it doesn't completely modify the band structure of the normal phase. Yeah. Thanks for the question. Yes?
Sorry, you're not saying that it wouldn't work for some superconductor that has like a mean field description. So this is like a strict limit on like that the pairing is perturbative relative to something else.
Yeah. Pairing is perturbative,
Okay.
Yeah.
Thank you.
Thanks.
Yep.
Okay, but that kind of story is about, that applies when you assume non-trivial pairing symmetry. But what I stress is that, so symmetry indicator implies topological crystalline insulator. So this, for this story, converse is not true. Even if symmetry indicator is trivial, there might be the case that your topology is still non-trivial, right? In particular, there is a recent, very, very important work done by this group, these people. And they say, even in the presence of time-master symmetry and inversion symmetry, even with conventional pairing symmetry, the superconductor can be non-trivial, topologically non-trivial. So although they study only a few examples of space groups, we found this is very interesting because it means that since the majority of superconductors in real world have conventional pairing symmetry, and even with conventional pairing symmetry, there is a case that the superconducting size is topologically non-trivial. That means that there might be a overlooked material. They are actually TSCs, but they're overlooked because they have conventional pairing symmetries. In order to look for this kind of example, we first have to know what kind of topological non-trivial superconductors exist for each space groups. Because they discussed only a few examples, we wanted to perform full classification for all space groups. So that is done in this paper. So we do some kind of K-theory type classification via so-called AHSS type scheme, which is also known as topological crystals. So in this scheme, you decompose your initial into 0 cell, 1 cell, 2 cells, and you place lower dimensional topological building blocks and see if you can realize gapped phases, right? And in particular, for superconductors, what is non-trivial is that for superconductors, if you place 2D TSCs in the presence of inversion symmetry, there appears some vortices, which is gapless. So there's some complication as compared to the standard topological crystal story for topological insulators. So we still worked out for classification of conventional pairing symmetries, and we found this kind of table for all space groups. And I don't go into the detail anymore, but so if you're interested, maybe you can ask Ono-kun for the detailed talk, okay? And let me move on to my second talk. So this is about fractional corner charges in trivial insulators. And this is done with Ono-kun and also Adrian, who is my colleague in Ashwin's group, okay? So famously, topological phases show some non-trivial signature in their boundary. So these topological insulators have helical edges on the boundary, and even the Haldane phase shows some kind of spin 1/2 degree of freedom at the end. So non-trivial bulk always implies non-trivial boundary, and sometimes the boundary is topologically ordered gapped phase, but still what is important here is that the boundary has some degree of freedom, like a gapless mode or topological order. And recently, this kind of correspondence is extended to a higher order one. So for 3D material, sometimes 2D surfaces are all gapped, but still 1D edges, hinges, or corners have zero, gapless mode or zero modes. And there are examples of this kind of material. And okay, this is interesting. And however, even trivial insulators sometimes show non-trivial signature on their corners. So in these papers, people realize that although the insulators are trivial, at the corner there can be charges, and the amount of charges is quantized to a fraction of unit charge. So not only topological insulators, but also trivial insulators sometimes show some kind of interesting phenomena on their corners. But what is different from the previous story is that here non-trivial signature are all like a gapless mode or zero modes. But now charge degree of freedom in this kind of trivial insulators are all frozen. So it's not a degree of freedom. It's just like some amount of charges sitting at the corners. But anyway, like we found this is interesting. But before we investigate this problem, I believe there was no materials for this kind of fractional corner charges. And we tried to find an example, and we found this idea of filling anomaly is very useful. So filling anomaly says sometimes a point group symmetry and charge neutrality cannot be simultaneously respected. So here I have an example of a 1D chain with inversion symmetry. And inversion symmetry says, so this white dot positive charge and black dot negative charge. And this inversion symmetry says, if I start from positive charge, positive, negative, then this inversion means that I have to end with positive charge. That means that total amount of charge in this system is not neutral, right? Like it's not zero. You have one additional positive charge. And you have two corners, so you naively expect that, naturally expect that we have fractional charge, 1/2, at each corner because of this inversion symmetry. And maybe in real material, you don't have this inversion symmetry, including corners. Maybe it is violated at corner, right? And charge neutrality is respected. But even in that case, you can expect the same charge configuration at one end, because like a surface charge or corner charge are local property. So the termination, detailed termination at the other end doesn't affect the charge at one corner, right? So using this idea, we found an interesting example, which turned out to be just a table salt, like sodium chloride. So in this example, again, the total charge in this system is 1 plus E, but you have 8 corners. So this means that from the idea of filling anomaly, you expect that you have 1/8 charge localized to the corner. So it was really surprising to us that like just product state, like ionic crystal, may still shows like a quantized and fractional charges localized at the corners. And our hope is that this is also experimentally measurable. Like you place some test charge at distance z from the corner, and you can measure the behavior of this Coulomb force acting on this test charge as a function of the distance d. Then our prediction is that if you go too close to the corner, you start to see the ions at the corner. So the Coulomb force behaves like like d squared over E over d squared. But if you are slightly far away from the corner, you start to see the cloud of like a localized fractional charge here. And there's a crossover from E over d squared to 1/8 of E over d squared. So this is this will be a proof of the quantized or fractional corner charges in this material. Okay, so this is the second part. Like even trivial insulator may still show something interesting. So finally, I want to briefly talk about my ongoing work about topological orders, but without ground state degeneracy. So I stress that like ground state degeneracy signals topological order, but their relation might still be non-trivial. And so let me explain the basic feature of topologically non-trivial phases. So usually topological ordered phases have ground state degeneracy. and fractional excitations called anyons, and their statistics characterize these phases, right? And we still have also like topological entanglement entropy in two-dimensional topological order phases, and these three are all related to each other. And the famous example is toric code. Like you have brackets and vertices, and you have loop operators, and that gives you topological ground state degeneracy, and blah blah blah. So this is a famous story. So today I want to discuss Zn extension of toric code. So first I want to define n-level spins. So this is just a generalization of famous Pauli matrices, right, to n-level systems. So I have 1, 1, 1, 1 for x operator, and 1 omega omega squared, blah 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 for z operator. This omega is 2 pi I over n, and they satisfy this commutation relation. Okay, so this is just a generalization of Pauli matrices. And I have a Hamiltonian, which is really just like a standard toric code. I have vertex term and bracket term. But here, vertex operator is not Hermitian, so you need to add a Hermitian conjugate. The same as this bracket operator. And here I have important parameter A. And I think when people discuss Zn extension of toric code, their standard choice is A equal 1, and that is discussed in this Kita's original paper. But the simplest non-trivial example is the case when A equal -1. So this model has been discussed in many papers already, but other values of A are also interesting. Okay. And what is important is that like vertex terms and bracket terms commute with each other. So this is like a stabilized Hamiltonian, regardless of the choice of the value A. Okay. And we have the standard string operators. But what is important here is that like a string operator cannot be just a product of x, 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 x. Because of this, power A, the string must be x and x to the power of A, and x to the power of A squared or something. And you have to design your string operators in a way that commute with the Hamiltonian, or in a way that it moves anyons. So these strings can form a closed circle only when this like a length system size L1 and L2 in the periodic boundary condition is a multiple of the period, right? And so in other words, like in these cases, like translation permute anyons. So ordinarily the anyons are such that like bracket have eigenvalue omega, but once you move it, the eigenvalue get modified to say this complicated power. So like a translation acts non-trivially on anyons. Okay. Then, for example, for the case A equal -1, if you work out, it's easy to convince yourself that the ground state degeneracy pattern is like this. So in the original toric code, which is the case n equal 2, in that case, we know that the ground state degeneracy is 4, regardless of the choice of the L1 and L2, right? But in this model, when n equal odd, and when L1 or L2 is odd, then the ground state degeneracy is 1. So there's no ground state degeneracy, so unique ground state with excitation gap. Okay. So you may ask whether this, this case, unique ground state with excitation gap, whether this class of, this sequence of this model is topologically ordered or not, right? But then you can compute topological entanglement entropy. So you have entanglement entropy, right? Like so this is ground state wave function, and you perform partial trace, and you compute this, standard von Neumann entropy, and you compute this topological part. Or you can form this kind of geometry like ABC, and you make some combination in which area part is doesn't contribute, like a Kita-F-scale type way of calculating topological part. And then you found that in this model, the topological entanglement entropy is always minus log n, regardless of the choice of A or L1 and L2. So this means that for this sequence, right? Suppose you keep L1 to be odd, and you change L2. If you happen to take that sequence of the system size, then you always don't find ground state degeneracy, but still your phase is topologically ordered. So I found this is very interesting, and it just originated from this behavior, this property like translation permute anyons, but I didn't know this happens. So I thought, for any topological order phases, we always find ground state degeneracy, but it was not the case. You can easily design this kind of stabilizer model Hamiltonian in which if you are unlucky, you cannot see ground state degeneracy. So this is kind of problem because in reality maybe if you don't know anything about your system, maybe you try first diagonalizing Hamiltonian for small size system size, right? But you don't see ground state degeneracy. But still, this is topologically ordered. So I found this is interesting. So this is actually the end of my talk. Yeah. So in conclusion, okay. So today I introduced our recent development of topological symmetry indicator method for topological superconductors, and we have a new database and subroutine. And I hope you use it and try to find a candidate material for topological superconductors. But I also revisited easy and simple criterion for topological phases. So okay, we know that symmetry indicator itself is not necessary for topological insulators, topologically non-trivial phases. And indeed, there are many examples of topological superconductors whose symmetry indicators are trivial, but still topologically interesting. So Majorana surface modes are available. Also, sometimes product states like trivial insulators shows interesting behavior, like corner charge of sodium chloride. Finally, usually people believe that unique ground state with gap is trivial, but it's not the case in some cases. And it depends on the choice of sequence of system size, but if you're unlucky, you don't see topological degeneracy on torus. Okay, thank you so much for your attention.
Okay, thank you very much for the very interesting talk. So, okay, so, yeah. Those questions?
So how did you conclude that Q total equals 1 for sodium chloride?
Yeah, so basically you need to count. So here, for example, this is a smaller version of this crystal. And you have 1, 2, 3, 4, 5, 6, 8, 9. That way, you can count, and you see that there's an additional 1 red point in this system. So 14 versus 13. Yeah. And that is guaranteed by the symmetry, right? So you have something at the center. So that is only 1. And all others comes in the multiple of 4 or 6 or whatever. So that must be odd integer. Yeah.
Okay, so Ben.
Okay, it's on. Okay. So with salt, I feel like ionic salts are super well studied in chemistry. So we always it should be surprising if there's something new in them. Has anyone ever said that this has been discovered and given another name in chemistry or seen before?
I don't know actually. I gave a talk in front of chemistry people, and okay, so there's a thing we need to worry about because in this kind of material. In reality, there's a surface polarization. So here I assume nothing happens in the surface, but actually there's a polarization pointing outwards in this kind of material. It doesn't affect the amount of charges at the corner. Polarization doesn't have charges, but still, it actually affects the behavior of Coulomb force. So my guess is that due to such kind of reason, actual behavior of Coulomb force is very complicated at the corner, and no one has ever seen it for that reason. But yeah, okay, I understand what you're saying. This is super old material, and if there's something interesting, people should have known it. But so far, I didn't hear such kind of story yet.
Sure, but it would also be interesting, like even if they had seen it, because no one thought of it this way. So it doesn't invalidate it. Yeah.
Thanks.
Thank you.
Yeah.
I guess just a follow-up question. Can you explain your mod E over 4 there?
Mod 4. Yeah. So, so that I think that is best explained by oh my goodness. Yeah. So there's a relation between say polarization and corner charge, and usually like modulo is integer, right? So in this case, you can modify the amount of charges at the corner by bringing additional charge at the corner, and plus E charge becomes minus E charge. And this way, like a surface decoration can change the amount of charges. So in this case, what I can do is to attach each plane's two-dimensional systems with quarter charges. So I said there are example of 2D system who has at the corner a quarter of charges, right? If I attach this kind of 2D material on the top of sodium chloride, actually I have 1/4, 1/4, 1/4 from 3 planes. So I modify the amount of charges by 3 quarters. So that way, like I have ambiguity. Actually, like, that means it depends on where you cut your system, right? So sometimes your amount of charge is minus 1/8. Sometimes it is plus 1/8. The difference is 1/4. So that's another way of saying this ambiguity.
No, but does it depend on how you cut it, or does it depend on the fact that sodium chloride might be impure?
Impure?
Impure
No.
in the
Even for pure sodium chloride, I think there's a
So you're saying the corner might be blue instead of red?
yeah. Wait. That is not the case. But yeah. Okay. I think that. It really depends on what you have in the middle, right? Like in the middle you have sodium or chloride. But
Okay, are you just saying if the corner is blue, it's minus E over 8? The Q corner is minus E over 8.
yeah, but like I feel like even if the center is a chloride or sodium, sodium ion, you can if you have another layer of this 2D layer of sodium chloride, you can modify it to a blue corner. So it really depends on where you cut. You don't have to change your bulk at all. You just put another single layer of sodium chloride, then it already get modified to like a minus 1/4.
Thanks.
I was just saying you have to mod out all the things you can glue.
Yeah,
and because
that's right.
and because it's 3D, you can glue 2D things,
That's
1D
right, that's right.
things,
That's what I'm saying,
and you
yeah.
can dope on the corners. So you
Yes,
have to mod out all of those.
Exactly.
And that's why.
Exactly. Yeah. But yeah. So that's like a theoretical understanding. But like physically, I was saying, just slicing out one single layer of sodium chloride will change. Yeah.
Next question, please.
So I have a question on the previous part on topological superconductor. So you say that the topology property can depend on the pairing mechanism. I mean, so what happens if the case that we have the two different mechanisms compete with each other? You say that can we change the parameter of the physical system so that you can have the topological phase transition by switching the dominant pairing mechanism?
Yeah. So in this kind of like a comprehensive database type research, we don't know anything about the detail of the system. So what we can do is to assume pairing symmetry and predict topological the topology of the superconducting inside, and that's it. So I'm not sure if I understand your question correctly, but
so for example, I know in some twist graphene system, you can have two different pairing mechanisms.
Right.
And then you can change magnetic field to switch the pairing mechanism. So do you say that in this case you can have the topological phase transition?
We cannot say this should appear or this should dominate, or we cannot say anything. So what we hope is that if the so you really synthesize the material and lower the temperature and in this transition to superconducting side, and you perform some measurement, and you see if the system is gapless or gapped, and then you go back to the this table to see if this assumed pairing symmetry is consistent with this gapped superconductor or gapless superconductors, and I want you to use this table to determine which pairing symmetry dominates in the assumed setting. But that's the only thing we can say. We cannot predict which pairing symmetry dominates for given parameters of the model.
Okay, thank you.
Sorry, we can discuss later. Yeah.
Okay, I think we have to move on. So let's thank the speaker again.
Thank you so much.